This is Alana Lynn doing the Motion of Falling Objects lab report. The main objective of this lab was to examine two objects, one that falls slowly and one that falls quickly, analyze their motion and tracker, and compare the output with the Python model. The result was that the models created to account for drag were much more accurate than the ones without drag, and the slow falling object experienced more drag. The fast-falling object I observed was a gel-filled stress ball. I filmed it being dropped and cut a section of right before it was dropped to when it hit the ground for tracker. That section was about 0.5 seconds long. I tracked the center of the ball as the center of the mass as it fell, and put the calibration stick on the ball as 9 centimeters. To simplify the calculations, I set the origin of the axis at the ball's initial position, and since it fell straight down, I left the axis vertical and lined it up so that the only change was in the y direction. The slow-falling object I observed was a section of bubble packaging, cut kind of like bubble wrap. I filmed it being dropped and cut a section from right before it was dropped to when it hit the ground for analyzing and tracker. This section was about 1.37 seconds long. I tracked the center of the rectangular piece and used the calibration stick of the bubble wrap, labeling it 15 centimeters. The axes here were also set to the origin, which was the initial position of the bubble wrap, but I angled them better to follow the path of the bubble wrap. It didn't fall straight down because it floated and spun a little as it fell. In Python, I used the information I gathered about the objects to create models better fitted for the situations. The mass of the ball was about 0.15 kilograms, and the mass of the bubble wrap was about 1 gram. Both had the same initial position of the origin and of initial velocity of 0 because both were started at the origin at rest. I chose a time step of 0.01 for both models because we wanted delta t to be small to get optimal results. To account for inside forces, I calculated the net force, which is the sum of all the other forces. In this simulation, we assumed the only outside forces were the force of gravity and drag force, which both act only in the y direction. The force of gravity is just the mass of the object times 9.81, then made negative to show that it's going down. Drag force is the negative ball velocity times the magnitude of the velocity times the drag constant. The velocity must be made negative because drag force acts in the opposite direction of the velocity. The drag constant varies according to the object, so this was adjusted until the model data fit appropriately for the actual data. For the ball, the drag constant was 0.001, and for the bubble wrap it was 0.008. To me, this seems like the bubble wrap's drag constant is still a little too small, but it fit the data, so I assumed there must be some small error in my tracker. To update the velocity, I added the velocity to the change of velocity, which was net force divided by mass and delta t. To update position, I added the current position to the velocity times delta t. In the graphs without drag, we assumed that there was no air resistance, so the velocity continually increases because there's no counterforce. This appears in the bubble graph without drag because the slope of the model is much steeper than the slope of the actual. In the ball graph without drag, there isn't much of a difference because the ball is heavier and a more aerodynamic shape, so the drag is really low. It's actually almost zero, and in this short amount of time, it doesn't have much of an effect. The y-intercept is the same in all the graphs because in every model and trial the objects were started at the origin. In the graphs with drag, the slopes are much more similar. In the bubble wrap graph, the actual data is curvy because it's flipping and turning, but the slope of the model fits the overall line. What if? What if the object was thrown down instead of dropped? How would this affect terminal velocity? If the object was thrown, the distance it would cover in the same amount of time would be greater because it would reach terminal velocity sooner, but drag due to air resistance is what affects the value of terminal velocity, so it's just the object's size and shape, not the initial velocity, that affects what the terminal velocity is. What does it all mean? The slow object's terminal velocity is only predicted by the model with drag because it is the drag that causes the velocity to have maximum and become constant. Thanks for listening.